Hi everyone, welcome to the last exercise class for this course. So today our plan is to simply formalize our pre and post selection logical paradoxes in a framework which will later be used in the lecture to make a connection of these pre and post selections paradoxes, which we have already seen on the examples of Hardy's paradox and also pigeonhole principle, to a phenomenon of so-called contextuality. So this will happen in today's lecture, but just as a precursor to that, we'll just go again through what we understand as pre and post selection logical paradoxes and make our definition more rigorous. And then maybe in the end, I'll make a couple of comments on contextuality and its connection to the paradoxes. Okay, so let us first recap what we mean by pre and post selection paradoxes. So usually the setting that we have in mind is we have a quantum system which is prepared in some state psi.
We can't see what you're writing.
Oh, sorry, I don't know why this happens all the time. Okay, now should be fine. Okay, this is weird. Let me stop sharing and try again. Yeah. Okay, so we have a quantum system which is prepared in a state psi. Then there is an intermediate measurement or a question that we ask, which is characterized by a projective measurement with the projectors Pj. And the set of these projectors we'll call M. And then it is followed by a final measurement so-called post selection in the, that includes the projector onto the state phi. So or we final measurement with post selection on state phi. Okay, so and then there are certain probabilities that we can write corresponding to this setup. So first is the joint probability for obtaining the outcome Pj, so one of these outcomes, and passing the post selection on the state phi in the end. So this is the probability P of getting the out of, so conducting an intermediate measurement Pj, post selecting on the state phi, given that the initial state, the pre-selection was on a state psi, and the total set of projectors of the intermediate measurement was M. So the probability is just, so first we project into psi, then we see the interlap with phi. Another probability that we can define here is, what if we don't want to focus on the particular projector Pj, but just want to see what is the probability of getting the post selection on a state phi given the preparation with a state psi over all possible projectors in the middle So it's kind of the marginal probability for passing the post-selection. So this we can write as just the probability of getting post-selection on a state phi given the pre-selection on a state psi and the total set of projective measurements in between, which is m. And this is basically just summing over all possible pj's. So summing over all probabilities above over all j's. And this will give us just this sum. Which means that now we can write the probabilities for the intermediate measurement.
Sorry, can you explain the notation? I don't understand the notation pj phi given psi m. Like the m is not part of the.
So m is the total set of projectors that we use for the intermediate measurement.
Okay.
So so it's like, of course, for this formula here, it doesn't matter. But for example, for this formula, for the marginal probability, we sum over all pj's in a set m.
Okay, sure. Yeah,
Yes.
okay. Thanks.
So we essentially, by this, we just specify which set of projectors we use in the experiment. Okay, and then probabilities for intermediate measurement, which are just the probability of measuring pj given the pre-selection, post-selection phi, pre-selection psi, and a set of projectors m would be just the ratio of these two. Just per definition of.
I think we lost you.
This is really annoying, and I don't know why this keeps happening.
And also, shouldn't the sum be 1 or? Oh wait, never mind.
No, because I mean we can choose phi and psi.
Yeah, but if they were the same, is it what's it called? P of m? Like.
I mean it's a projective measurement.
Yeah, but is it like complete that it should add up to 1 if you look at the same state?
I mean not necessarily. Like it can be any set that you would like to have. For this, like here we're just writing stuff for a very, very general situation where it's not necessarily complete, but later we'll actually consider a much simpler structure of M where we would have just one projector and identity minus that projector.
Oh, okay, cool.
So here we just have the ratio of these two. This is just per definition of conditional probability. And so here we would have this formula. Okay. So again, this is very general. We'll consider a particular example just later in the class. And now let us simplify this general construction by just considering a following set of projectors. So we just simplify by saying that our set of projectors is just projector P and identity minus B. And so basically we're only considering intermediate measurement on two outcomes. And then let us write the probability of getting the projector P given psi and phi and Rm as just the probability of P psi phi and the probability of phi given psi and our set of projectors as just probability of phi given psi. So now we only assume that this is the only set of projectors that we consider, and we know P. Okay. Then another assumption that we will need to make is the following. We assume that P, the probabilities of measuring projector P, given the pre and post selection psi and phi, are, so they're either 0 or 1 for all projectors that we have. And we also assume that P, the projectors that we choose, belong to some set of projectors, which is a finite set of projectors, and is closed under completeness, which means that if P is in this set, then 1 minus P is also in this set. So this is, and I stopped showing again. Okay, so, and this finite set of projectors P is different from the set of projectors M that we considered before, because M is just about the projectors that we use in a particular run of the experiment, but P is about the projectors that we can choose during different runs of the experiment. So, for example, the set of projectors M can be something like, so is the pigeon in the box number 1, or is the pigeon not in a box number 1? And the set of projectors P can be something, it can include questions like, is the pigeon in a box 1? Is the pigeon in a box 2? Is the pigeon in a box 3? And so on. So these are two different things. And the reason why we choose the probabilities of measuring the projector as only 0 and 1, because first we want to make only statements which are certain. So statements which hold with probability of 1, in order to kind of make our paradoxes stronger, because like if the paradox includes statements which hold only with probability less than 1, then like you can always say, it's only there is still some probability for the statements not to collide. So this is important, and this is also important for the purposes of logic, because usually when we connect stuff to logic, in logic we have a set of propositions, so the statements that we can make about the world, and then usually what is assigned to the statements is so-called interpretation, which is a function assigning a truth value to the statement. And when we think about the truth value, we only think about, the sentence is either true or is false. And this is how classical logic works. Of course, there are other types of logic, such as, for example, fuzzy logic, where the truth values can take any value between 0 and 1, but this is quite an exotic consideration and usually not used. Okay, so now we would like to exactly connect. oh yeah, before we connect it to the logic, let us do the following construction. So we have our finite set of projectors, but let us make sure that this finite set of projectors is good to put kind of an overlaying logical structure over it. So we need to extend our set of projectors to so-called partial Boolean algebra. Which is generated by P. So this is basically a smaller set of projectors that we can find. Which we label as P prime, such that P belongs to P prime, and the following conditions are satisfied. So if P belongs to P, so it's some projector, yeah, I know it's, just hold on a bit. Yeah, if P belongs to P, if P belongs to P prime, then 1 minus P also belongs to P prime. And the second more important one is that if P and Q belong to P prime, and they commute in a sense that PQ equals QP, let me actually, does it only happen in this version? Okay, sorry. Let me copy what I've done here and put it in the other program, because I feel that because I updated to a different version, it keeps crashing. Okay. No, this is not what I want. Okay, so if P and Q commute, so that PQ equals QP, which kind of means that it doesn't matter in which, suppose that we're making both measurements, P and Q, and then if PQ equals QP, then it doesn't matter in which order we do the measurements. Then essentially we get that PQ also belongs to P prime. And you see that even if the first condition is already fulfilled by the initial set P of the projectors, because it's close under the completeness, then the second condition is not necessarily fulfilled by P. So we just need to take all the commuting projectors from the set P and complete the set P by adding their products PQ. And what is the meaning of these two conditions? So the meaning of the first condition is, for example, if we associate a certain proposition to each projector, or a certain answer to the question that the projector holds, like for example, is the pigeon in a box 1? Then like by measuring the projector corresponding to this question, you get the answer to the question, which is yes or no. So this means that we can ask the question itself, but we can also kind of negate the question. So ask the exact opposite of the question. So for example, if we have, is the pigeon in a box 1? it means that we can also ask, is the pigeon not in a box 1? And so it kind of ensures our ability to perform negation of the particular proposition. And the second property, it ensures that if we have two questions which commute with each other, so we can ask them in whichever order we want, then we can also conjunct these two propositions. We can also complement these two propositions, or we should be able to complement them because they commute, and so nothing actually physically stops us from just asking both of these questions in a row.
Can you give an example with the cat in the box?
I'll give
Yeah, sure.
I'll give an example in the end. Would that be okay?
Yeah, perfect.
Okay. Now all this very abstract talk was coming to the probability functions that we assign to this projectors. So we need to extend our probability function from the finite set of projectors P to the set of projectors P prime. And so we initially have our probability assignment as f of P is just the probability of measuring P given the pre and post selection psi and phi. And when we extend it from a set of projectors P to P prime, we need certain algebraic conditions to be satisfied, and each of them has a very straightforward kind of meaning interpretation. So the first condition is that for all P's in P prime, f of P lies between 0 and 1. This is straightforward because the probability is always between 0 and 1. Then the probability assignment of the identity element is 1, and the probability assignment of the 0 is 0. So, which makes sense because we can always kind of measure the identity, and that would correspond to probability of measuring identity 1 because we always measure identity. And for all PQ, which belong to...
I hate to break it to you, but it happened again.
Ah, this is really annoying.
So I think what the problem is that you're sharing it over your Mac, so you're sharing it to your Mac.
Yes.
I also got a problem inside, like updated some software, I don't know what, but if you install Zoom on your iPad, then you can also enter a meeting for your iPad and you don't join with audio. And then you can...
Yeah, I know, but yeah, the problem is that, okay, let me...
I mean, that's probably too much work now, but...
Yeah, I know. It's just that I bought a new iPad, and on the previous iPad, it worked well. It's just like,
yeah,
it's funny
like
that...
update, that could be...
Okay, so for all PQ, so for now, I'll just try to refresh it every once in a while, and just let me know when it does not share. Okay, so for all PQ and P prime, such that PQ equals QP, so for these which commute, then we need to be able to kind of apply usual probability rules, as in like f of P plus Q minus PQ equals f of P plus f of Q minus f of PQ. So it's like, it's the same that you, for example, would write for two sets P and Q and kind of their intersection. Okay, and the idea is that if such assignment of probability is not possible, then so if the assignment of if these three properties cannot coexist for a particular setting, then the predictions for this set of projectors P form a logical pre and post selection paradox. So the idea here is that such a probability assignment does not exist. Okay, now let us go to the example. Okay. So, okay, so the example we're going to consider is a bit different one from the ones that we considered before, but it's of the same spirit. So it's called a 3-box paradox. And the idea of the 3-box paradox is the following. So we have 3 boxes, 1, 2, and 3, and then we have one ball. And the ball has, and the Hilbert space of the ball is spanned by 3 options, which are it is in the first box, it is in the second box, and it is in the third box. And then we have 2 states on which we will post select. Okay, so it's a 3-box paradox. So we have a ball. Hilbert space is spanned by states 1, 2, 3. And we have 3 boxes. 1, 2, 3. And we pre-select or prepare the ball in a state psi, which is the equal superposition between being in 3 boxes. And so this is pre-selection. And then we post-select on a state phi, which is this state. Okay, and first the description of the paradox that we get having this the pre and post selection for the states. So we first ask the question, is the ball in a box 1? So this question corresponds to the set of projectors M, which has 2 projectors. The ball is in a box 1, so we just project it into box 1, or the ball is not in a box 1. So the second projector is the same as 2, 2 plus 3, 3. Okay, let us calculate the probability. So we need to calculate the probability of having the ball in a box 1, given the pre and post selection on a states psi and phi. So according to the formula that we established before, it's the following ratio. So it's the denominator is phi 1, 1 psi modulus squared, and the denominator is just the sum over all projectors. The same thing, but for all projectors in M, which are only 2 terms, right? So first term is for the projector 1, 1, and the second term is for projector identity minus 1, 1. Okay, so let us calculate this. So here I'll have 1/9 because I'll have 1 over square root of 3 here, 1 over square root of 3 here, and then that would give me 1/3, and squared will give me 1/9. And then inside the modulus, we would have just this. So this is phi, the projector 1, 1, and this is psi.
Can you reconnect it?
Okay. Yeah, so here we have 1/9. Then we have this is phi, this is our projector, this is psi squared. And in denominator, we have first the same thing, which is 1/9 and the denominator, plus also 1/9, 1 plus 2 minus 3. And here we write identity minus 1, 1 as 2, 2 plus 3, 3. And here we have, again, 1 plus 2 plus 3 squared. Okay, so denominator, except for this 1/9, will actually give us 1 because the only non-zero elements of the sum would be if we take 1 from here, the projector, and 1 from here. So it's going to be 1. So here we also have 1 plus, this is going to be actually 0 because the only non-zero elements would be 2, 2, 2, 2, which give us 1, and then 3, 3, 3, 3, which give us -1 because we have minus here. So it's going to be 0. Essentially, so we get 1. Which means that the probability to find the ball in a first box is going to be 1. So another question that we can ask is the ball in the box 2? And this question corresponds to the set of projectors M, which will be 2, 2. The ball is in box 2, or N1 minus 2, 2. The ball is not in a box 2. So if you consider the similar calculation we did above, so the probability of,
I'm sorry, did you just say that the probability of a particle being in box 1 is 1, or what's that is 1 mean?
oh yes.
Okay, but you start out in this.
So essentially, again, we are back to this pre and post selection setting. So I have a ball which I pre-select, which I prepare in the state psi, and then I post-select in the end on this state phi. And then I can ask the questions about my ball in them, like an intermediate questions about my ball. Like, for example, a question, is the ball in a box 1? And if I calculate the probability of the ball being in a box 1, given this, given the pre-selection on the state psi and post-selection on the state phi, by the formula we got in the beginning, I get the probability with probability 1 that it is indeed in a box 1.
But yeah, if you do the same for 2, then you get the same thing, right? Like,
yeah, for 2 you get the same thing. So here you get again this instance of the pre and post selection paradoxes, and yeah, you have the ball somehow in a box 1 and in a box 2. So exactly, so the probability for finding it in a box 2 would also be 1. So is the ball in both boxes. And this is exactly about, so the logical contradiction here is exactly about that. What we are trying to do logically when we start to analyze the situation is to assign every projector, as in like every question, a particular probability. So we assign to the question, is the ball in a box 1? The function f, which corresponds to its probability, which is 1. Then we make the similar assignment for the question, is the ball in a box 2? And if we have these two assignments, this is in contradiction to the logical rules that we have established, because the logical rules that we have established, in particular, the third rule says that if we have two projectors P and Q, such that PQ equals QP, then we are able to kind of, then with respect to this PQ, we have the following thing for their probability assignments, which should hold. And here, for this particular situation, we even have an easier situation where if P is 1, 1 and Q is 2, 2, then PQ equals QP equals 0. So essentially, what we just need to check is if f of P plus Q equals f of P plus f of Q. And here we get that f of 1, 1 plus 2, 2 equals f of 1, 1 plus f of 2, 2 equals 2, because both of them are 1. But this is not possible because the probability assignments can only take values between 0 and 1. And hence we get kind of this logical paradox. So this whole conversation about like this values assignment is essentially about thinking, okay, so I have a system, I can ask any question about the system given this pre and post selection. But then somehow all these questions have to live in the same framework and their answers have to be consistent with the respect to each other. So it's like, for example, in a normal classical situation, if I ask a question of, is the ball in a box 1? And the answer is yes. Then if I ask another question, is the ball in a box 2? The answer should be no, like it has to be no. But kind of this observation simply points to us that some questions, when we come to the quantum setting, some questions are just simply not compatible. So for example, like not compatible in this usual logical sense. Like here, the question of, is the ball in a box 1 or is the ball in a box 2?
How do you check this compatibility? Because it's not a commutation relationship, right? Or is it this like checking role 3?
I mean, so here you can only check just by computing.
Okay.
I mean, for every pre and post selection, like if you have any setting with a particular pre and post selection, and this pre and post selection are non-orthogonal, then you can always find two questions which would be incompatible. So you can always find like this logical paradox in there.
Mm-hmm.
Yeah. Yeah, and this intuition also in the lecture will be connected to so-called contextuality. And contextuality is it's a property of a theory, which quantum theory has, which basically is about, again, values assignment, but values assignment when it is locally consistent, but globally inconsistent. So as an example of a contextual setting, we can take the Penrose stairs. Like if you ever seen this construction by Penrose, you see that. So it's basically, I think I even drew it. Let me try to find it somewhere. Yeah, so here we go. So for example, so we have this Penrose stairs. So this person is higher than this person, like is located higher than the first person. This person is located higher than the second one. The fourth is located higher than the third one. And so by all kind of, if we connect globally their statements, then the third person, so the fourth person has to be higher than the first, but in this construction, it's not true. So this is a good example of kind of system which is locally consistent. So if we take, for example, the first and the second person, the second person is located higher than the first, and the third person is located higher than the second, and the third person is located higher than the first. So it's kind of for every two of them, the statements that they make are kind of, they make sense. But when we look at this, at the system of the sentences globally, then we just discover an inconsistency that we cannot really deal with. And in this sense, this construction is contextual.